Hello everyone, welcome back. So let's start out our first example. So what does it give us? Oop, there you go. So we've been given a 4 kilonewton load, which is applied at the end of this beam, and it's supported by pins at A and C. We want to figure out the support reactions at A and C. Okay, so you notice it doesn't give us a coordinate system, so you're going to need to set your coordinate system, which I would suggest making it along this beam, and then, of course, a vertical direction. Second, we need to determine if there are any two-force members. Well, this one right here looks like it's going to be a two-force member because it's only connected at 2 points. This one, three-force. 1, 2, 3. Draw a complete free body diagram of the boom, and then apply the equation of equilibrium to solve for the unknowns. Okay. So we've got a whole lot of information here, and hopefully you can solve it. So I'm going to let you go off on your own and try this out. So pause, and in 3 seconds I want you to come back, and hopefully everything went well for you. So 3, 2, 1, and we're back. So let's try this out together. First off, we have to draw our free body diagram. Now you may be wondering, well, wait a second, this is a pin, so shouldn't it be like, you know, an X or a Y and an X component? Well, yes. However, that would mean we would have 4 unknowns and we wouldn't be able to solve them. Luckily, this is a two-force member. And we know the direction of the line of action between D and C. And we know that with a two-force member that the force that goes through that connection must be directed along this line of action. And so we know the direction of this force, even if we don't know the magnitude. So you could break this up into 2 components. You would just then have to use a free body diagram right here to solve. So we're simplifying it by realizing this is a two-force member. We know the direction, we just don't know the magnitude. Okay, with that in mind, with this one right here, we have no idea about its direction or magnitude, so we have to break it into 2 components. We have all of our forces. We have 3 equations, 3 unknowns. The first thing you're asking yourself is, which one should I solve for first? Well, my advice is always this. Start with X and Y and look, are there multiple forces pointing in the X direction? There are. Don't start there. Are there multiple forces pointing in the Y direction? There are. Don't start there. Is there a point that I can take the moment around that would get rid of some of my unknowns? Well, I could do it around point C, and that would get rid of this. But it still leaves me 2 unknowns. However, if I do it around point A, neither one of these has a moment because it's around point A, and that leaves me with just 1 unknown. So it seems like taking the sum of the moments around A would be the best way to start. And that's exactly what they do. So we have 2 components, one from the 4 kilonewton force and one from force CD. Remember, since this is a horizontal distance, I only need the vertical component of the force. So that's why we have a sine of 45 here. And I'll go ahead and draw that just to make sure that's completely clear. As a note, since it's 45 degrees, you really could have done anything you wanted there. But in this case, it looks like they were using the 45 degrees as right here. And so that's opposite over hypotenuse. So opposite over hypotenuse is sine. That's why it's sine of 45 degrees. And then we notice the distance is different. It's only 1.5 meters to where C is applied, but it is 3 meters to where the 4 kilonewton force is applied. Second, you notice our signs. This one's going down, which is causing a clockwise moment, and this one is pushing up, which is causing a counterclockwise moment. You can decide which one's positive and which one's negative, so just go with that. So we do so, and we solve, and we get that force CD is going to be 11.3 kilonewtons, which makes things easy because then we only have 1 unknown per equation. Some of the forces in the Y, only that one's unknown. Some of the forces in the X, only this one's unknown. So you see why we should have calculated that first. I would honestly do some of the forces in the Y after that point because you already have the Y component of the force right here. Like you've already calculated it to solve some of the moments around A. But in the end, it's not that difficult to solve either way. And you see this is what we had, this component from earlier to get our Y component. And then when we saw that we get negative 8 kilonewtons for the reaction force at A in the x direction, and negative 4 kilonewtons for reaction force at y, at A in the y direction. Now notice the negative sign, which means that I drew these arrows in the wrong direction. This should have been to the left, and this should have been down. And that makes a lot of sense, because if you think about trying to hold a plate or something else, if you have one finger pressing in the middle, and you've got one finger pressing on one of the edges, you need a second force to press on the other edge to keep it balanced. And conversely, if you have a force pushing this direction like we do from force CD, we need another force that's pushing in that direction. So don't worry about it too much. If you get it wrong on your free body diagram, it will just come out as negative like you see here. Okay, that's enough for this one, and we'll jump into a little bit harder problem next time. See you then. Bye-bye.